Right. Right. Testing. Miss Shabila, can you hear me? Boleh dengar ke?
Boleh doktor?
Boleh. Okey. Alhamdulillah. Terima kasih.
Sama. But when you have
Right. Assalamualaikum warahmatullahi wabarakatuh, and a very good afternoon to everyone, ladies and gentlemen. We are about to begin this session, so please stand by. And I would like to seek for your kind cooperation to avoid any visual disturbance during the live broadcast session. If you have any question, the conference resource personnel are ready to attend you at the reception desk. And thank you for your kind cooperation and attention. So we will start at 3:40 p.m., which is approximately 5 minutes from now. Thank you. Okay, all right. So it's already 3:40. I think we can start now. Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And a very good afternoon, ladies and gentlemen. Welcome to the first Malaysia International Conference on Nanotechnology and Catalysis, MICNC 2021. We are now in this session, parallel 3, okay, for graphene, fullerene, carbon nanotubes, cellulose, and fiber. My name is Rohaida, and I am a lecturer at the University Technology Mara. I will be the session chair today, together with the session moderator, Madam Azima. I invite all the invited speaker and presenter to request share audio and video now. Right, as an announcement, so ladies and gentlemen, the oral presentations will be evaluated for the awards under 2 categories, which is the best session presenter that will receive the certificate for best presenter, and I will announce at the end of this session. We have Best Presenter Award that offered prize money from 500 to 1,000 Malaysian ringgit, trophy and award certificates. This will be announced during the closing ceremony. I would like to seek for your kind cooperation to mute your microphone if you do not presenting and to avoid any kind of visual disturbance as possible. For those who intend to ask questions to presenter, you can channel your question in the Q&A box. I will read it after every presentation. You can also request to share your audio and visual to ask your question in live mode. Presenters are given 15 minutes for presentation and 5 minutes for the Q&A session, whereas for the invited speakers are given 25 minutes for presentation and 5 minutes Q&A. I will remind, or the committee will remind the presenter to end the presentation 2 minutes before the presentation session ends. And if, let's say, the presentation sessions has exceeded the 5 minutes allowed, so it will be stopped to allow for another presenters. So before we start this parallel session, so I will appreciate it if everybody can turn on the camera for the photo session. So can you please switch on your camera?
1, 2, 3, smile. Okay, thank you.
Okay. All right, thank you very much. Okay, without further delay, okay, you will be hearing the presentation from our first presenter. Our first presenter today will be Ms. Hairul Zakirah binti Abu Bakar. She will present her research and findings on a systematic review on the physical, chemical, and absorption properties of activated carbon synthesized from different biomass for dye removal application. Please welcome.
Okay. Hold on a second, yeah? You can hear me, right? Okay. Okay, can you see my screen right now?
Yes.
Assalamualaikum. Assalamualaikum warahmatullahi wabarakatuh. First of all, thank you to the moderator, chairperson, participants, the committees, and members of the floor. I'm Hairul Zakirah Abu Bakar. I have recently completed my undergraduate study in biochemical biotechnology engineering at IUM. I'm happy to be here today to enlighten everyone with my study entitled A Systematic Review on the Physical, Chemical, and Absorption Properties of Activated Carbons Synthesized from Different Biomass for Dye Removal Application. So this is actually my final year project, and for information, the material in focus in this study is on the activated carbon, which in the recent studies can be used as the support material for the incorporation of nanocatalysts onto these activated carbons for maybe improvements in dye removal application. But in my scope of study, it is focused on the support material, which is the activated carbon itself. Agriculture remains as an important sector of Malaysia's economy, contributing to 12% of our national gross domestic products. From the wide expanse of agriculture products, millions tons of waste are generated annually, such as rice husks and coconut shells. This abundant biomass waste, rather than disposing them to the landfills, we could make use of them by turning them into activated carbons that can serve in various applications, such as in wastewater treatment. Activated carbons are used as adsorbents to remove toxic substances from wastewater coming from various industries that can achieve up to 98 to 99% of removal due to its highly porous structure. However, this method, compared to other available methods such as coagulation, it is not commonly selected due to the relatively higher cost of current commercial activated carbons. Therefore, this is where the abundance of these biomass waste can be used as an alternative to produce low-cost adsorbents. In this review, the target application is on the dye removal from textile industrial effluent. Textile industries takes up to 54% of the industries that are responsible for the presence of dye effluent in the environment, and the majority part of the effluent that is harmful to the environment is the dye. So among thousands of dye as part of the components, methylene blue dye is an example that represents the synthetic dyes in most studies, and therefore the reason why the selected dye is this and we'll focus on in this review. Now, looking at the significant increase in the number of published papers in the area of activated carbon synthesized from biomass and screening through them, a research gap was found that leads to the current review. Recent studies from 2015 to 2020 are lacking in comparative studies in the physical, chemical, and absorption properties of the activated carbon synthesized from these different biomass, although there are many experimental data available from the current literatures. So this makes way for a systematic literature review using the available data and to produce a significant discussion on them. This can also improve the understanding on the relationship between these activated carbon synthesis conditions and the physical-chemical properties to their absorption performance in dye removal application. Therefore, in order to reach to such understanding, this study was aimed to achieve four main objectives as follows, which was first to identify the research trend in activated carbon production from biomass and to select three of the potential biomass for dye removal application. And next, reliable sources must be screened and only relevant papers were selected for the analysis of the activated carbons synthesized from the selected biomass. With the extracted data, the effect of the synthesis parameters onto their physical-chemical properties was analyzed, which then will lead to the identification of the correlation between these properties to their dye absorption performance. To achieve the objectives mentioned, here is the general flow of the applied methodology. Some of you might not be familiar with the systematic literature review since it is not commonly done for studies of biochemical engineering background for myself. So I will delve a little bit into that to expose the methods involved in producing a systematic literature review. To produce the systematic literature review, only relevant papers needs to be selected. Therefore, based on the identified gap I've highlighted earlier, research questions were formulated based on what is known as the P-Quark analysis to guide the information that shall need to be extracted from the selected literature. The main research question that needed to be answered that I've established in this review was, what are the differences in dye absorption performance of the activated carbon synthesized from different biomass for the wastewater treatment application in Malaysia? On top of that, sub-research questions were also formulated to ensure the necessary information are gathered to answer the main research questions. To select the three biomass sources, a trend analysis based on the number of patents and scholarly works were obtained from lens.org and Science Direct databases, which were selected due to their reliability. After multiple refinements, the recommended search string for article screening through Scopus database was developed as follows to be applied during the literature screening. Next, the inclusion and exclusion criteria that was developed beforehand was then applied to select or reject the papers for full article viewing and data extraction. The data on the physicochemical and absorption properties from the selected articles were then extracted as of these parameters and then analyzed to answer the established research questions. So part of the information gathered is that Malaysia has contributed to quite a significant number of published studies on activated carbon synthesized from abundantly available local biomass sources. Malaysian institution has shown to have contributed more than 30% of the papers on the activated carbon synthesized from palm oil anti-fruit bunch, palm kernel shell, and durian shells, which are the biomasses that can only be found in Asian countries like ours as compared to other biomasses which are readily available in other countries. So this is a significant number and explains the possible reason in the lack of papers published on the activated carbons from these three biomasses throughout the years. Therefore, the current number of published papers when considering these three biomasses might not be sufficient yet for the current review, which requires a more extensive data on their physicochemical and absorption properties. This is supported by looking at the data on the number of published papers collected from lens.org and Science Direct databases. There are a significantly smaller number of papers on the three biomasses, and the majority of them are more focused on coconut shell, rice husk, and bamboo instead. This signifies the increasing interest by the science community in using these biomasses to synthesize activated carbons, especially in Asian countries. Therefore, the three biomass sources, coconut shell, rice husk, and bamboo, were selected for this review. To further analyze the performances of these activated carbons from these three biomasses, data from research papers were extracted and analyzed. This diagram shows the number of papers recorded for each phase of the literature screening. Out of 190 papers found initially using the recommended search string, only 93 papers were selected for the full text screening, and after applying the inclusion and exclusion criteria, only 44 papers were selected focusing on the selected biomass activated carbons, were fully reviewed for the full analysis. So, different types of biomass, when synthesized into activated carbons, will form different distributions of surface area and pore structure, and these differences are reflected to their dye adsorption performance. Carbonization temperature and holding time are the two synthesis conditions that have shown significant effect onto these properties. So based on the extracted data, it can be seen that all three biomasses could be synthesized into activated carbon of similar ranges of surface area and pore volume at different carbonization temperatures. Bamboo could be carbonized in a wider range of temperature from as low as 40 to 800 degrees Celsius compared to coconut shells and rice husks with a more limited range as follows. However, looking at bamboo activated carbons, a significantly higher surface area of 2,000 to 2,300 meters square per gram could be achieved at very low temperature around 105 degrees Celsius. This is possible when the bamboo were carbonized in a vacuum condition, which resulted in more mesopore formation, which may allow for higher amount of methylene blue dyes particles diffusing into the larger pores. It was also observed that rice husks are more suitable to be carbonized at temperature around 450 to 500 degrees Celsius. This is because at higher temperature, the micropore structure of the rice husk tends to destroy easily, which will result in lower surface area available as absorption sites for the methylene blue dye absorption. Now, looking at the effect of holding time. In general, the common practice for activated carbon from the tree biomass was mostly capped at 1 hour. However, looking at bamboo activated carbons, the surface area and the pore volume significantly increased with longer holding time that could result up to 2,200 meters square per gram and 2.3 centimeter cube per gram, respectively, at 10 hours of holding time. The higher number, this is because this happens because a wider pore distribution and significantly more pores were formed, especially mesopores, with longer holding time. The higher number of pores and wider distribution resulted in a more porous structure, thus increase the overall surface area and that's available for the dye adsorption. The holding time for rice husk activated carbon could also be reduced from 1 hour to 30 minutes and yet resulting in a higher surface area and pore volume than average. This was possible by the use of phosphoric acid during chemical activation that can remove the high ash content in pores of the rice husk effectively. In the end, after washing the synthesized activated carbons, larger pores were left behind, which increased the overall surface area and the pore volume. Now, the graph shown here are the percentage of maximum methylene blue dye removal by the activated carbons across different surface area and pore volume. The percentage removal was normalized by the dose of activated carbon used, the dye concentration, and contact time during the adsorption process to make the data comparable from one another. It was observed that there was a trend in the dye removal capability in which, if you can see from here, at higher surface area and pore volume, more methylene blue dye could be removed. On average, the bamboo, coconut shell, and rice husk activated carbons could achieve a percentage removal between 0.3 to 1.6% when the surface area and pore volume were kept within these following ranges. However, there are exceptions in which the maximum dye removal could be increased beyond the average values up to 10% or even more for coconut shell activated carbons. So looking back at the data, the high maximum dye removal will increase up to 10% for all the activated carbons and even more for coconut shell activated carbons when surface modification was incorporated. The use of steam or chemical activation resulted in the increment of the bamboo and coconut shell activation coconut shell and bamboo activated carbons' pH. So higher pH has shown to be suitable for higher absorption of cationic dye since there will be less competition between the dye and the hydrogen ions in an alkaline condition. Furthermore, for rice husk activated carbons, by pH adjustment, the basic pH around 8 to 11 resulted in a negatively charged surface, thus increases the absorption of the positively charged methylene blue dye onto the activated carbon surface through electrostatic force attraction. So through this systematic review, we have seen that based on the recent research trends in terms of available publications and patents, bamboo, coconut shell, and rice husk are among the top potential biomasses that could be synthesized into activated carbons for the application of methylene blue dye removal in Malaysia. we have also seen how different synthesis conditions, particularly carbonization temperature and holding time, played the role to produce activated carbons with different surface area and pore volume. These differences in the properties in the end will lead to the differences in the methylene blue dye adsorption performance, where higher surface area and pore volume resulted in higher dye adsorption. Furthermore, significant improvement in methylene blue dye removal could also be achieved by activated carbon from different biomasses through their surface modification using external agents such as steam or chemical activation and pH adjustments. All in all, we can say that the physical, chemical, and adsorption properties of the activated carbons synthesized from these three biomasses could be the next commercialized low-cost adsorbents to be applied in the dye removal application from wastewater effluent. Finally, there is another aspect to be highlighted from this study. The current industrial enterprises and municipalities using commercialized activated carbons usually require regeneration and reactivation as feasible solutions to decrease their carbon footprints and also their production costs. However, the studies from the research papers are lacking in the information on the reusability of the synthesized activated carbons from these biomasses, which I believe could be further explored and beneficial in the future to be included as part of the activated carbons' developmental studies for contaminant removal and also commercialization potential. That's all for me. I hope the information delivered today could, if not many, just a little bit useful for everyone regarding my focus of study. Thank you very much.
Okay. Thank you very much. Okay, Ms. Hairul Zakira for a very excellent and nice presentation. So I'll open the questions for the speakers. You have any?
Okay. Yes, I have one, Dr. Rohaida Yasmin.
Yes, please.
Good job, Khairul Zakira. I like how you deliver your presentations. And in the previous research, you said that they have used a bamboo, right, for synthesis by using sulfuric acid, right? Why you choose that? It means they have a lot of abundant and acid. Why you choose the sulfuric acid compared to the nitric acid, let's say?
I'm sorry, which one? Which part are you focusing on? Sulfuric acid?
Yeah, why you use the sulfuric acid rather than other acid? Because in the lab we have a lot of abundant of acid, right? So why you choose the? But I see the previous slide you use the sulfuric acid.
Can I ask you which slides were you referring to? Because I'm not sure which one. Is it
this one, right? I think this one. Phosphoric acid.
Yes. This one is actually for rice husk. This is actually from the papers. They have mentioned that when they use phosphoric acid, because of the high silica content inside of the rice husk ash that is formed during the carbonization process. So what works best for removal of silica inside the pores is that using phosphoric acid, when it reacts with the silica, it can easily be removed by washing them after with water, and therefore leaving the larger pores behind, and which is what we want because we want higher surface area and pore volume, which was achieved by having these larger pores.
Okay, so this previous the paper he mentioned the phosphoric acid, right?
Yes.
Yes. So after this, you want to synthesis? It means you want for the bamboo, coconut shell, and rice husk. You want to synthesis all the material, or you just focus for, like, say, for the bamboo, or the coconut shell, or the rice? You want to synthesize the activated carbon, right?
Yes.
After this, you go to the lab. So what are you focusing on, or you want to synthesize all that biomass?
Oh, yeah. If I had the opportunity to actually go into the lab and actually produce these activated carbons, in the initial plan was actually to actually synthesize all these three biomasses, these three activated carbons from these three biomasses, and then produce an analysis to compare the properties of these activated carbons. But then due to the inability for me to go into the lab, and that's why instead of doing that, I get the information from the current databases to make this analysis. But if I had the opportunity to do so, of course, I would want to test onto these three different activated carbons and actually see for myself what are the properties that we can get, and also the performance with the dye removal application.
So you want to test all the biomass? Okay.
That's what maybe if you have the concern that I might not know of.
but it's okay. That's good.
Uh-huh.
You do have it show you a trigger to do your research. That's good. Okay, Dr. Roida, that's from me. Good job.
Thank you so much.
Okay, thank you
Dr.
very much.
Rohaida, John here.
Yes, please.
I want to know very good presentations. Actually, it's good that you didn't go to lab. You do a literature first before you go to lab. Okay, that's good lah because really good. I think if you not, then you have simply go to lab and do something else. This is not correct. You do the literature first. Normally, this is a practice. Okay,
Yeah.
back to your questions. I look at the your absorption capacity. Is it based on Langmuir or fluidish? Because in the absorptions, right, you
Yes.
have two what I call isotopes. One is the
Mm-hmm.
Langmuir and one is the fluidish isotope. When you make a comparison, do you compare the Langmuir or fluidish, or when your slide, you remember the slide that you compare the absorption capacity or absorptions percentage?
Yeah.
Actually, there are three. One is Langmuir, fluidish, and
Mm-hmm.
also they have this maximum absorption capacity, which
Yeah,
you
yeah.
compare with. So must be careful. You need to take care
Mm-hmm.
when you compare this result. Which one you comparing?
For me, instead of focusing, I did actually extract the data from in terms of the isotope, whether it is Langmuir, Friedrich, but then the one that I've used for this analysis in terms of the maximum dye removal percentage, which means it's not the absorption capacity that is related with the what do you call the isotopes, right?
Yep.
So yeah, because of the lack of information on that in the papers that I've gathered, so instead, the maximum dye removal percentage was used as the basis to compare the performances, and to make it comparable. The percentage removal was normalized. The data was normalized to ensure to incorporate the what I call process conditions of like different dose of active carbon used, the concentration used, and
Okay.
also the contact time.
Okay, I just want to have some advice.
Mm-hmm.
If you need to, this column is good, but add another column for the Langmuir absorption isotopes, because it will tell you the absorption capacity, milligram per gram. That means how much dye is absorbed per gram of your material, the bamboo, coconut shell. That's more representative.
I
Normally,
see.
follow Langmuir, lah, right? But you put
Mm-hmm.
another column that if you follow Fenrich, you have
Mm-hmm.
another extra two column. So when you do your experiments, that is what people looking at. Yeah, so it's more accurate because you put in the
Mm.
isotope, you have to fit to the isotope.
I see.
That's more
Okay.
accurate in terms of comparison. Okay, thank you.
Okay, thank you for that.
Okay, thank you very much to the presenter and also for the to the audience for a very insightful comments and also suggestion. So thank you very much, Ms. Hairul Zakira. So I'm
Thank
afraid
you.
that we don't have much time and we need to go to the second presenter. So thank you very much. So now we would like to welcome to our next presenter. So please welcome Miss Nur Shafika Jasmi. Okay. And Miss Nur Shafika Jasmi will present her research on the first reports on cellulose production by an indigenous yeast, Pichia kudrevzevai. Hopefully I'm pronouncing it correctly. Okay. USMYBP3 isolated from a rotten pineapple, isolation, characterization, and enhancement. So please welcome Ms. Rashafika. The floor is yours.
Thank you. Is it clear?
Yes, it is on the screen.
Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and very good evening to the respected chairpersons, the moderator, and also to all the participants. I am Shafika binti Jasmi, and my topic for my presentation today is on the first report of cellulose productions by an indigenous yeast Pichia 3ZVUS and YBP3, which was isolated from rotten pineapple. Plastics. They are everywhere around us. It's in our furniture, in our clothing, even in our soup. And it's not that hard to understand why, since plastics are very cheap. They also are very easy to shape into whatever you could want. Also, they have a lot of exciting properties that could make very useful for us in different situations. And for that reason, we also make a lot of it. In 2020 alone, the global plastic productions total about 367 million metric tons. That is 1 year. Imagine from this massive amount of plastic production, and we keep producing it more and more every year. By the way, about 40% is used for packaging. For example, like the wrapper of the candy, its contents are gone, but the wrapping is still persists, and still persists, and that will last for centuries unless it's burnt or recycled. So why do we use a packaging that lasts for generations just to protect a product that lasts mere minutes? It's just an absurd, right? So we need a solutions. That's when our research come into a picture. Since our group is working on bio-nanotechnology, and the nanomaterials that we have been working on recently is a potential for plastics or food packagings. And what's really neat about it? You don't have to travel far to find it. We just have to go out for our door from any plants that can be Malaysian forests. We have a lot of those, right? Or it can be from the waste product from agriculture as well. Also, it can be from the microorganism as well. We can produce something that's called nanocellulose. This nanocellulose consists of the tiny fibers, tens of thousands of times thinner than human hair. Moreover, nanocellulose also can be divided into three main subcategories, namely cellulose nanocrystal, nanofibrillated cellulose, and also microbial nanocellulose. In addition, nanocellulose usually looks like a gel. It looks like a gel. However, once it dries, these tiny nanofibers that are in gel attracted to one another, they can bind very tightly together. And how tightly? Tight enough to where oxygen's molecule can readily go from one side of nanocellulose to other. And it's better at stopping oxygen in plastics actually. And that's what really important since oxygens can degrade food that we want to store. And that's why we use plastic in food packaging in order to protect from oxygen in the air. And basically we can say that nanocellulose actually does the job better than plastics. So the purpose of this study is firstly to isolate, screen, and identify for the potential biocellulose producing microorganism. Secondly is to develop medium formulations in order to enhance the biocellulose production. And lastly, to characterize the biocellulose. This is the overall experimental workflow of this study. Started off with the sample collections and preparations of pineapple and also banana fruits, and then proceed with the isolation for BC producing microorganism via serial dilution and also strict plate techniques on the H3 shrimp agar, and then the isolates that were successfully isolated from the HS agar were further screened by nourishing them into HS medium broth, as this HS medium was used for cultivations, maintenance, and also screening for the stream-producing cellulose. And then the minor potential for the biocellulose producing microorganism was then identified by the morphological characterization and also molecular analysis. And let's proceed with the fermentation part. Before the fermentation part takes place, prior inoculating the cell culture into the production medium, the inoculum was prepared first, and then proceed with the productions of biocellulose using one factor at one time approach. Three different variables were investigated in order to enhance the biocellulose productions, which were carbon source, nitrogen source, and also culture conditions. And then the best conditions from the one factor at times per approach study were further evaluated using a two-level factory design approach. This two-level factory design approach was used to screen and also evaluate the significant factors of the carbon source, carbon concentration, nitrogen concentration, and also inoculum size towards the biocellulose productions. After the fermentation part done, we proceed with the harvesting and also purifications of the produced BC. And the strong acid hydrolysis of the BC were further used to extract the bio-nanocellulose from the selected isolate. Before subjected to the characterizations of the produced bio-nanocellulose, the bio-nanocellulose was sonicated, homogenized, and also freeze-dried first before going to characterization of the produced bio-nanocellulose. As for characterization of the produced bio-nanocellulose, two types of analysis was done, which were morphological analysis via SEM and also TM analysis, and also structural analysis via FTIR and also XRD analysis. Moving on to the result part, for objective number 1, isolation, screening, and also identifications of cellulose producing microorganisms, a total of 5 isolates has been successfully isolated from the rotten fruits. And then only 2 isolates that show a pellicle formation after cultivated into the HA's broth for after 2 weeks. And then after 5 days of cultivations, only isolate USN YBP1 shows a pellicle formation with a weak floating network pellicles, and also isolate USN YBP3 with a strong thin rigid membrane pellicles. From this study, it was found that formations of pellicles on the surface culture medium indicate the ability of microorganisms to produce cellulose. As the isolate USN YBP3 shows a potentials of the biocellulose production with the strong characteristics of the thin rigid membrane pellicles. Hence, the isolate was further characterized by a morphological characterization. Based on this photo, it shows that the cell is in the ovoid to elongate shape. And then the molecular identification also was further conducted. And from the blast analysis, it shows that this isolate is belong to the Pichia kudrezii species. Over the last few decades, lots of bacterial nanocellulose has been well documented. However, there are no previous reports that are available on the cellulose production in shake class, particularly for this species. Apparently, this is the first reports of the cellulose productions for Pichia kudrezii. Hence, its formation can be included into the cellulose field, as Pichia kudrezii can be an alternative candidate for the current cellulose producers nowadays. For objective number 2, productions of biocellulose by Pichia kudrezii USN YBP3 strain via one factor at one time approach. As for selections of the carbon source, 3 different carbon sources were investigated, namely glucose, sucrose, and glycerol. And based on the data presented, it shows that the highest BCUs was attained when glucose was employed as a main carbon source, since glucose is a simple sugar monomer that can be transported easily and also directly in during the cellulose production process without any molecular breakdown. As for nitrogen source, 3 different nitrogen sources, which were peptone, casein, hydrolyzate, and also amino sulfate, was investigated in order to enhance the biocellulose productions. And based on the data presented, it shows that peptone, since peptone consists of very plentiful of nitrogen compounds, so obviously the highest BCU was attained when peptone was employed as the main carbon source. And then as for culture conditions, the effect of agitation intensity was investigated by changing the agitation speed from static to 200 RPM. And then from the data presented, it shows that the highest BCU was attained under agitated culture at 200 RPM, since in agitated cultivations, the oxygen is mixed continuously, hence resulting in higher BCU compared to the static cultivation. So based on this finding, it shows that this strain, which is a Pichia kudrezii, is more suitable for the agitated cultivation. Hence, this strain can be applied into a large-scale aerated and also agitated fermentation system to produce a biocellulose. And then the best condition from the one factor at one time study were further evaluated using the 2-level factory design experiment. In this experiment, 3 types of different variables, which are glucose concentration, peptone concentration and inoculum size were tested at different level, which were low level and also high level, which in this case, glucose concentration were tested at a low level of 2% and high level of 8%. And then moreover, peptone concentration were tested at low level of 0.5%, also high level of 2%. And lastly, for inoculum size, it was tested at a low level of 5% and also high level of 10%. And the dependence variables for this study is a PC yield, of course. And all this experiment was conducted under cultivation conditions of a temperature at 30 degrees Celsius at 200 rpm of agitation speed for 4 days of cultivation periods. And based on this study, it shows that the highest PC yield and also productivity was attained in the set 8 with the 8% of glucose concentration, 2% of peptone concentration, and also 10% of inoculum size. Further determination using the Pareto chart analysis show that only nitrogen concentration and also carbon concentration give a positive effect towards the biocellulose production, since orange color indicate the positive effect. Meanwhile, inoculum size give a negative effect towards the biocellulose production, as the blue color indicates a negative effect. Lastly, for objective number 3, as for characterization of biased nanocellulose produced by pitch-check residue SNYBP3, for scanning electron microscope, from this photo, it shows that the image of the surface morphology of membranous pellicles formed by pitch-check residue SNYBP3 show an interwoven network of cellulose fibers. It also can be indicated as a biocellulose. And then proceed to the transmission electron microscope. To the best of our knowledge, interestingly, this is the first report on the novel and also unique spherical bio-nanocellulose that was extracted from the micro-bio-nanocellulose. And then as for FTIR analysis, it shows that the FTIR analysis from BNC from this pitch-check residue strain show a very similar profile to other bacterial species of bio-nanocellulose. And lastly, for X-ray diffractions, the BNC bio-nanocellulose produced by pitch-check residue SNYB3 consists of the highly ordered crystalline regions and also amorphous regions with a high crystallinity index that was which was estimated by up to the 82%. Lastly, as a conclusion, we can conclude that our findings substantiate that this strain USNYBP3 show a very remarkable production ability of biocellulose, and of course with a high degree of purity of 82% that can be further applied in various fields of applications such as medicine, food, and textile. And hopefully from what I show you today can give a little hope on the gloomy path of today's wasteful reality. I also would like to acknowledge the Ministry of Higher Education Malaysia and also USM Research University grant. Thank you.
Okay, thank you very much for the very nice presentation. Okay, so now I would like to open for the Q&A session. Right.
Hi, no, Shafika.
Yeah.
John here. Hey, I just want to know on the your bacteria.
Yes.
Yeah, is it a new species? Have you done the genome sequencing to look at the bacteria? If a new bacteria, you can name the bacteria yourself, though.
Oh, but it shows 100% similarity to the other species.
I see.
From
So
the
it's not a
database.
new species.
Not really new species, but it's the first report on the yeast cellulose producing.
Unfortunately, because
yeah.
if you found a new one, you can name it your under your name.
Yeah.
Yep. Previously, I also extract something and then it's cannot found in the database. You can name it as what you want. Okay. Further look at it, right? This application in the biocellulose, are you mean when you do the hydrolysis, is it the raw material or you use a cellulose to become a nanocellulose, or is a raw material like a food empty food branch, then you apply the bacteria? Which one? Yeah, that's why I want to clear it.
From this study, from the sample collections of fruit, rotten fruit, I isolate the yeast, and then I produce the biocellulose using any carbon source or nitrogen source, and then from that cellulose, in order to extract the biocellulose, I apply the strong acid hydrolysis. But when compared the photos or the image of before and after treatment, it shows that there's not that really different, a significant difference. So I think maybe after that we can exclude the extra strong acid hydrolysis.
That means you say that the source of this is not a biomass, a glucose that but transform the glucose to about cellulose. You're trying to say.
Yeah, I think presumptively we can say that maybe
Okay.
this is an extracellular cellulose from the yeast strain itself.
Yeah, yeast you mean the yeast? That means you transform a glucose to cellulose.
Yeah, correct.
Okay. That's clear. So it can be also transforming from just now you share different source. For example, the glycerol also can be transformed into a cellulose.
Yeah, correct.
Okay, interesting. Is it first report transforming glucose to cellulose?
There have been many reports, but on the bacterial nanocellulose, but this is the first one report on the yeast producing cellulose.
Oh, so this is the first report on the yeast producing.
Yeah.
Okay.
Accidentally, we found a yeast that can produce cellulose.
Okay.
It's
Thank
good
you,
news
thank you.
for us.
Okay, understand now. Okay, thank you.
Okay, thank you so much.
Okay, thank you for the question. Do you have any questions from the floors? If not, maybe I can ask one question. I want to know about the stability of the cellulose that being produced. So do you have any work or maybe experiments performing about the stability of the cellulose being produced, maybe in terms of towards acidics or any other experimental conditions?
Oh, not yet. But now we are working on to check the stability of the nanocellulose. By maybe we can check like a TGA based on TGA analysis, thermogravimetry analysis, and also water holding capacity, and then maybe see the crystallinity index as well, polymerization index. And now we've been working on recently.
All right. So the stability test will be your future directions of this research, right? All right.
Yeah. Thank you.
All right. Okay. Thank you. It's a very nice
Thank you.
presentation. Okay.
Okay, thank you.
So thank you. For today we actually only have two presenters, and now I think we would like to continue with our next presenter, our invited speakers. Okay. So. Let's see. So our invited speakers will be Dr. Nurul Izaila Alias. Okay, so she will talk about the reliability of graphene floating gate flash memory cell with the high K, low K tunnel barrier. So, Dr. Nurul Izaila.
Yes.
The floor is yours.
Can everyone hear me?
Yes, Doctor.
All right. Okay. Assalamualaikum and a very good afternoon to the chair session, also to the moderator and the other participants. I am Nurul Izaila. So today I will be presenting for MICNC the topic entitled Reliability of Graphene Floating Gate Flash Memory Cell with High K and Low K Tunnel Barrier. So I'll be switching a bit from the experimental from the past two presenter, and now my work is more on the simulation and modeling. All right, so this is my presentation title. So I'll start my presentation with the background of study, the objective. So basically, this is the postgraduate student work of mine. And then I'll continue with the objective of work, the device simulation setup, and then the results and discussion is divided into two: device validation and reliability of graphene floating gate flash memory. Finally, I will conclude my presentation. May I know what are your view? Is it presenter mode or audience mode? Can you see full screen?
Yes, you
Yes,
can see the full screen.
but my as long as you can see full screen. Okay, all right, sorry about that. So let me continue my presentation. I will continue on the background of study. So what is flash memory? So flash memory is a non-volatile memory, a device that can electrically program and erase. So we have our for example, our hard disk, we can save the data and we can delete the data. So that is one of the flash memory. So in semiconductor memory technologies, we have two types of memory, volatile memory and non-volatile memory. So in this presentation, I will only focus on the non-volatile memory. So non-volatile memory itself has two types, PROM and MROM. So there are several types under these subtopics. So my presentation will be focusing on the flash memory. So in these figures, it actually shows demand in flash memory technology nowadays from past 1995 to 2015, as we can see from here. The size of memory, or we take a simple example as a hard disk that we have been used in the computer. So the size of that memory is kept increasing. Now we have 1 gigabyte of the size memory. Okay, so the other background that we can relate the technologies of memory is where we can closely relate with the Moore's law. Okay, so when we talk about according to the Moore's law, so this red line is actually the Moore's law, where the average, actually the number of transistors will be double in every 2 years. If you can see that the other lines other than the red lines here is actually the innovation or the technology of memory. So we can see the trend of memories from 1995 to predicted to 2025. The trend is actually following the Moore's law. So in here we can see that when the size of the transistor decrease, we be able to produce larger size of flash memory. So this is the background of 3D flash memory architecture. So how to produce, the fabrication of flash memory. Okay, so we have two types, 2D flash memory, which is the past being used of the flash memory, and nowadays already been switched to 3D flash memory. So in 3D flash memory, actually it able to overcome the short channel effect. So when we go to of course we go to basic in flash memory, it will be used when we talk about Moore's law just now. So we talk about a single transistor. Of course, to develop the memory, we might need that transistor. So that is the very basic. Okay, so when we talk about transistor, we may talk about the short channel effect, the effect that may arise when we reduce the size of transistor due to the Moore's law just now. All right, so the short channel effects may occur. So it may reduce the performance of memory. So the researcher came with the 3D flash memory. So this 3D flash memory has been reported that it may it may actually overcome the problem of short channel effect. All right, so these figures is actually for the 2D flash memory, it is consisted of only one layer of memory string. Okay, this one. So for the 3D flash memory, as we can see, whereas here we can see the memory cells are stacked into multiple layers. Okay, so the fabrication process named punch and plug fabrication process. So this stacking is actually due to the punch and plug technology. Okay, so there are difference between these two types of memory. So in this in 2D flash memory, it has high density memory, which is presented by smaller patterning techniques. However, in this 3D flash memory, with this punch and plug fabrication process has been fabricated by two major industry, which is Toshiba and Samsung. They actually did this punch and plug fabrication process. What they found is in 3D flash memory, high density memory is presented by the layer stacking here, and smaller patterning techniques for the vertical channel. All right, we go again with the background of the flash memory. So when we talk about flash memory, memory inside the computer or the hard disk or any memory, so we may want to talk about the reliability. How long can the memory stand? It can be used for up to 10 years, or it is better if we can use more than 10 years or to 20 years. So this study is to actually study how long the graphene-based flash memory may last. It's more than 10 years, or it can be extrapolated more than 20 years. All right. So when we talk about the flash memory reliability, there are only two parameters that is important, which are the data retention and also the endurance. So what is data retention? So data retention in memory is the capability to retain memory over specific time. So this study is actually to study these two what we call it as the characterization, the data retention and the endurance. So endurance is the capability to retain memory after certain number of program erase cycle, which is we save, we delete, we save, we delete, how long it may that the cell can withstand. Okay, all right. So how we actually measure the data retention? It is actually from this figure. This is the results from past from the literature review. So how they measure the data retention is by actually so they simulate. So in this case, they in this paper they did both on the simulation and the fabrication. So what they did is they have the graphene-based flash memory also, okay, the graphene-based flash memory FET. All right, so they actually measure where they apply program voltage with 10 volt and the erase voltage negative 8 volt. All right, so what they did is these figures is actually indicates the threshold voltage shift, okay, versus time. Okay, so the time is actually applied to their graphene-based flash memory is from 10 to the power of 0 up to 10 to the power of 4. So they actually give the program, and then they measure the threshold voltage, and then the erase, they measure the threshold voltage. So that is the repetitive process, okay, to find the threshold voltage. Okay, so what they did is only up to 10 to the power of 4. Okay, if we increase the cycles of program and erase, so we might take a longer time. Okay, so what actually been done by Toshiba, by Samsung is extrapolation method. So they did up to 10 to the power of 4 second program and erase, and then they extrapolate up to 10 to the power of 8. So 10 to the power of 8 is approximately to 10 years. So they see that this is before they apply program and erase, and this is they actually extrapolate or they projected up to 10 years. So this is the remaining threshold voltage shift occurred in their graphene-based flash memory. Okay, so this is where the study begins. Okay, so the next one is the endurance. So endurance is the capability to retain the memory after certain number of program and erase cycle that the cell can withstand. Okay, so this is quite different from the data retention. So what they did in this is the threshold voltage shift also versus the program erase cycle every cycle. So this is over time for the data retention. For endurance is cycle, program and erase cycle. So what they did is up to 10 to the power of 4 cycle. So what is the remaining threshold voltage shift after this cycle? So this is what we call it as memory window. So this memory window, so this is also memory window, and this is also the memory window. So the concern is to see how much the memory window may last after the extrapolation of 10 years, how much the memory window and charge loss after the 10 to the power of 4 program and erase cycle. So this is the literature review. So this is just a part of the summarization, okay, from all these key paper, 5 papers. So of course they have a very strength on their research, okay. So of course they also developed the floating gate with graphene, all the paper with the single layer graphene, and also multi-layer. They also compare with the multi-layer graphene. So in this work we'll be focusing on the multi-layer graphene. floating gate graphene base with multi-layer graphene, right? So their strength, of course, they have wide memory window and so on. They have high data retention. However, the shortcoming that we may say about this paper is they lack on the endurance study. Okay, they have a very strength. Their strength is on they have wide memory window, and they did up to the data retention. However, they didn't do on the endurance. Okay, so here come the objective of the work. Okay, so to virtually fabricate and analyze the memory performance characteristic of graphene based floating gate flash memory cell in terms of data retention and data endurance. And the second one is to study and analyze the reliability of graphene based floating gate memory cell by using variable oxide thickness varied technology combination with different high K materials in terms of data retention and data endurance. All right, so this is the scope of work. So this is the simulation and the modeling study. So the study is divided into two: device validation and device performance. So for the device validation, of course, before we did further on the simulation and the modeling, so we validate our structure, our simulated structure with the experimental result, okay, where we keep close with this experimental result that which has been published by A. Mishra 2014, and then we analyze the validation and validate the results. Okay, for the device performance, and this work compare between the N-channel doping and also P-channel doping, and finally is to study the performance of program erase characteristic, number of electrons stored, data retention, endurance, and also charge loss. So for the device simulation, basically for the general flow is focusing on the device validation, and the second one is the performance of memory cell with different high K materials. So it consists of two parts actually. So this is the simulation, the simulated floating gate graphene based memory cell. So this is how the structure look like. Okay, it has substrate, okay, and also the tunnel oxide, the floating gate, the blocking oxide, and also the control gate. So this is basically the basic structure of floating gate memory cell. So in this work, what it's made different from the other work is instead of using tunnel oxide, which is conventionally is the silicon dioxide, but in this work, the oxide, the tunnel oxide is actually the combination of high K material and silicon dioxide, where high K material is on top of the silicon dioxide. So this is the different from the other works. Okay, so the type of high K material in this work is silicon nitride, aluminium oxide, hafnium oxide, and zirconium oxide. So these all four high K materials will be compared. Each of them will be compared. So this is what we call as a variable oxide thickness, the varied technology. All right, so if I go further, so for the device simulation itself, so this is the structure dimension. So this in order to make a fair validation and fair comparison with the experimental work, what we did is we actually replicate what this paper has fabricated. So we actually design the simulated structure based on their dimension. Okay, so this is the maximum possibility that we may get from their work. Okay, so the gate length is about 600 nanometer, and the tunnel oxide for their work is 8 nanometer for silicon oxide, but in this work also 8 nanometer for silicon oxide, and blocking oxide also same. The rest floating gate thickness, control gate thickness, silicon substrate doping, and source drain doping also has been set with the same dimension as in the experimental work that's been published by A. Mishra. So next is to get, since their tunnel oxide is solely or by using conventional silicon dioxide, but in this work we we first validate with the tunnel oxide first, okay, and then after we validate the IV characteristic as is validated and perfectly matched, then only we move to the varied technology where we change this conventional tunnel oxide to the varied technology, which is the combination between high K material and low K material. Of course, low K material is silicon dioxide. So from this, after that, we move to the characterization. Okay, so basically this results shows the threshold voltage versus programming time and threshold voltage versus the erasing time. So in this case, program and erase is 20 volt and 14 volt for erase. So it is the work is repetitive to the different voltages. Okay, so this is the N channel. This is for the P channel, compact between these two. So for the data retention, okay, as we compact between the substrate of channel as N channel and also P channel. So for the PE operation, N channel able to get the memory window of 15.4 volt and P channel able to get the memory window of 15.6 volt, which is not much different between P channel base and N channel base. So this is because the superiority is considered to the N channel because N channel has the majority carrier of electrons, okay, while P channel have the whole as the majority carrier. That's why electron has higher mobility and it has a little bit higher in the memory window. So these figures is actually same like what I have shown in the earlier slide of the background of study. So this is the data retention figures, okay, shows the threshold voltage versus time, same like in the past in the literature review where we did on the 10 to the power of 0 up to 10 to the power of 4 program and erase. Okay, after that we extrapolate to 10 to the power of 8, which is about 10 years extrapolation. So from here we get that for the N channel, it able to get 11.6 volt memory window, and P channel able to get 11 volt memory window. This is after 10 years of extrapolation or 10 to the power of 8 second. Okay, so in this case, we may say that for N channel graphene based floating gate memory, it able to retain about 75%, and for P channel, it's able to retain about 71%. Okay, so now we talk about the variant. Okay, so after the validation work, okay, which has been matched with the IV characteristic and also the PE cycle and everything. So now it comes to the variant. Okay, for the performance of flash memory, the variability work has been done. So these figures is actually showing the result for threshold voltage shift over time for 4 different combinations. So combination that I meant just now is between high K material and low K material. For the low K material is silicon dioxide and high K material is silicon nitride, aluminium oxide, hafnium oxide, and zirconium oxide. So this ratio is actually the ratio of low K material and high K material. So this is representing the ratio of low K and high K material. I mean the thickness and also the size. So this shows these tables is actually summarize the results from here. The best ratio is 1:7, which is 1 nanometer is low K dielectric, which is the silicon oxide, and 7 nanometer is the high K material. In this case, 4 high K materials are compared, okay, and the barrier height is as in this list here. So the memory window that able to achieve for this combination of ratio 1 nanometer to 7 for 4 different high-K materials are 23 volt, 20 volt, and 25.4 volt, and 26.0 volt, which is quite impressive. The memory window retained for this combination of variant. Okay, instead of using just a silicon dioxide, when we combine with a high-K dielectric, or the technology called is a variant technology, we able to get the maximum memory window more than 20 volts. So in this case, the silicon dioxide and hafnium oxide, the combination of silicon oxide and hafnium oxide and silicon oxide and zirconium oxide with low barrier height is with lower barrier height. Okay, this one for the hafnium oxide is about 1.5 electron volt barrier height, and zirconium oxide is 1.4 electron volt barrier height. So in this case, it's easily to tunnel the electron, okay, through the floating gate channel. Okay, as compared to these two combination. So, however, out of these 4 combination, it is found that the silicon dioxide and zirconium oxide, the combination of these two has the highest memory window compared to the other high-K dielectric. Okay, so finally, the data retention with variant. Okay, after it is found that the best 2 combination, which is between aluminium oxide and also zirconium oxide. So these two combination has been extended further, the simulation for the data retention. Okay, for all 4 materials combination. With the stress, with the gate stress negative 1 volt to 1 volt. Okay, again the same simulation has been done. Okay, for the conventional one, and now is for with the variant technology. It is found that from these results, okay, I just summarize what happened here. So again, it has extrapolated up to 10 years or 10 to the power of 8 seconds. So the remaining threshold voltage that is important that we want to see, or the other name is the memory window after 10 years of extrapolation. It can be seen here. The combination of silicon dioxide and aluminum oxide retained 83% threshold voltage, which is about 16.6 volt. Okay, and the combination of silicon dioxide and silicon nitride, okay, retain 56%, and the combination of silicon oxide and hafnium oxide retain 47%, and silicon oxide and zirconium oxide retain 33%. So from here, it may be said that the combination of silicon oxide and aluminum oxide retain the highest memory window after 10 years of extrapolation, which is about 83%. So we may say that the aluminum oxide with the K value about 9.3 and the band gap about 8.8 electron volt has been investigated, and it can be said that it is the most suitable candidate for the tunnel barrier flash memory cell with graphene base. Okay, next is the data endurance, which is we can't compare with this data endurance with the other study, because other study just up to this data retention. So the data endurance, why data endurance is important? Because we want to see the endurability of the graphene-based floating gate memory cell. So what has been done is the cycle, the repetitive cycle of program and erase, okay, from 10 to the power of 0, 10 to the power of 1, 10 to the power of 2 until 10 to the power of 4. Okay, so we just focus on the aluminum oxide and hafnium oxide. Okay, so in these two, these two has been compared. Okay, as the combination of silicon oxide and aluminum oxide retain 82%. However, the silicon oxide and hafnium oxide retain 75%. Again, for the data endurance with variant technology, the combination of silicon oxide and aluminum oxide graphene-based floating gate memory cell has the best results, okay, which can retain the highest memory window, which is about 82%. All right. So in this case, we may conclude that silicon oxide, the combination of silicon oxide and aluminum oxide tunnel barrier demonstrated better endurance characteristic compared to the silicon oxide and aluminum oxide. And silicon oxide and aluminum oxide, this combination tunnel barriers taught lower charges compared to the silicon oxide and hafnium oxide. And we may say that it increased the charge stored, okay, may increase the chances of the leakage current after some period of time if we have intention to further extend up to more cycle. Okay, let me conclude my presentation. So in this presentation, graphene as floating gate memory cell is successfully simulated and validated with experimental work, okay, by using a varied technique, okay, variable oxide thickness technique for 4 combination low K, high K material, which are silicon oxide with silicon nitride, aluminum oxide, hafnium oxide, and zirconium oxide. The memory window for flash memory without high K material able to get about 15.4 volt memory window. However, with the application of combination between low K and high K materials, which is the variant, able to get more than 20 volts of memory window. Okay, the data retention of 4 high K material has been studied. It is found that the best candidate for combination for graphene-based floating gate memory cell is silicon oxide and aluminum oxide, which able to get 83% data retained after 10 years of extrapolation, which is about 16.6 volt. Okay, and the endurance reliability, which proved that the endurance retains 82% and 75% respectively for combination of silicon oxide and aluminum oxide, and silicon oxide and hafnium oxide tunnel barrier for 10 to power of 4 PE cycle or program erase cycle. Thank you very much.
Right, thank you very much, Dr. Nurul. It is a very interesting presentation. Okay, so now I would like to welcome any questions from the floor. All right, anyone? Okay, so I do have actually maybe 2 questions, Dr. Nurul. So I must admit that this is a very new topic to me, and I have definitely not an expert on this field, but I think that it is very interesting, okay, to gain a new knowledge on this matter. So I have 2 questions. Number 1, if I look into the slide just now, if I'm not mistaken, in terms of the memory window, the silicon dioxide, zirconia dioxide has the highest memory window, but they are producing the lowest data retention. So maybe you could explain why such a case happened?
For this one?
Yeah, and if you refer to, I think, the previous slide mentioning about the memory window.
Okay, okay.
I think from the memory window, it's showing the highest, I think. It is.
Yes, correct. Okay. So why? So why we didn't proceed with this? Since zirconium is oxide able to get the highest, but zirconium oxide, the material is has the high the high K material is has the highest number. So if we have planned to fabricate, so zirconium is not suitable because it's due to the high K value, it may not suitable for the fabrication because it is too hot. So we go to the second option, which is the hafnium oxide and also the aluminum oxide. But still, although the other material, the other combination of material is not as good as the zirconium oxide, but at least it able to get data retention more than 20 volt memory window.
All right. So is it because of the temperature that it also producing the low data retention as like on the
for this case, for this study, it's just at room temperature, but temperature do affect the memory window performance. If we want to apply, if we want to do further reliability tests or the stress gate test, we may need to put at high temperature, and the temperature also may affect the performance as well.
All right. Okay. Thank you. And my last question will be, I just wondering whether there is any threshold value for the data endurance and retention, or the memory window to be considered as, okay, this is good, this is not good. So is there any, or it's just like, I mean, the higher the value is the better, or is there any like threshold value?
I think the memory window in terms of the voltage shift is hard to say as a threshold or benchmark point, but because it is also depends on the material, on the structure used, but if we may say that the best is if we may get the data retention percentage is more than 80%. I might say that, yes.
Okay, all right. So is it possible for us to achieve 100%? Just wondering. Is it possible?
Impossible.
Okay. All right. Okay.
All right.
Okay, thank you very much. So it's Dr. Nurul for a very nice presentation. So I think we have come to the end of this session. Okay, so congratulations and thank you to the presenter and also to everyone who participating in this session. So now I would like to announce the best presenter for the session. So I am very honored to announce the best presenter for this session of I think Graphene, CNT, Fullerenes and Fibre is Miss Nur Shafiqah Jasmi. So congratulations, Miss Nur Shafiqah Jasmi. Right. Okay. Now we are reached at the end of this session, and thank you for all your participation. On behalf of the MICNC 2021 Organizing Committee, I would like to seek for your kind cooperation to fill up the feedback form as given by the session moderator in the chat box. And you are invited to join the rest of the event, okay, and hope to see you again. Thank you, everyone. Have a nice day.
Thank you.
Thank you.
Thank you.
Thank you very much.
Thank you.